In 7.1, we talk about Laplace transform. So the Laplace transform is an integral transform. Okay. Suppose you have function f of t. You just multiply that by e to the negative st, and then you integrate with respect to t for the whole thing from 0 to infinity. And that's called the Laplace transform. That's the definition. So given a function ft, you can get its Laplace transform under proper conditions. And then we also discussed some basic properties for Laplace transforms. The Laplace transforms of several simple functions. Okay, we covered, polynomials, exponential functions, and sine cosine functions. I believe the Laplace transforms of those functions. Now, when we try to use Laplace transform to solve a differential equation, first we just take the Laplace transform of the equation on both sides. So we get another equation of A's, an algebraic equation. We can easily solve this algebraic equation, to get f of S. We call the Laplace transform of f of t by capital F of S. So we can solve that capital F of S, and then what we do, we just take the inverse Laplace transform to get it back into the domain of t, and in that way we solve a differential equation. Okay, or actually, more generally, or more precisely, we solve an initial value problem. Okay, so then we need to know what it means by inverse transforms and the transforms of derivatives. Okay, so when we try to, change back from S domain to T domain, we need to take the inverse Laplace transform. And when we convert the differential equation into algebraic equation, we need to also take the Laplace transform of derivatives of functions. So we need to discuss the topics of transforms of derivatives. So there are two topics in this section. So first, let's just talk about the inverse transforms. So suppose we have a function small f of t, and we take the Laplace transform, we get capital of S, so it becomes a function of S. And so we just say that the small ft is the inverse Laplace transform of capital S. Okay, so the capital F is the Laplace transform of small f. Conversely, we call small f the inverse Laplace transform of the capital F. So this is just a terminology, just like derivatives and antiderivatives, very similar. And we write small f of t equals script L inverse, or -1, if you like, of capital F of S. All right. So the way to find the inverse transforms of Laplace transforms is just very straightforward. You just go backward from the Laplace transform. So for example, we know the Laplace transform of the constant function f of t equals 1 is 1 over s. So then, by the definition of inverse transform, we say 1 is the inverse Laplace transform of 1 over s. So this is exactly what we did with antiderivatives. Okay, so the theorem, on this page just tells us some inverse transforms based on the Laplace transform from the simple functions we discussed in last section. Okay, so basically these are the same formulas we had in the previous section. You just rewrite it in terms of inverse Laplace transform. Okay, but just rewrite it backward. Okay, so for example, the inverse Laplace transform of n factorial over s to the n plus 1 is t to the n, where n is all natural numbers. And we know that because we already found that the Laplace transform of t to the n is just n factorial over s to the n plus 1. And also, we got the inverse Laplace transform of 1 over s minus a, which is e to the at, the inverse Laplace transform of k over s squared plus k squared is sine kt, and the inverse Laplace transform of s over s squared plus k squared is cosine kt. The inverse Laplace transform of k over s squared minus k squared is just sin kt. Lastly, the inverse Laplace transform of s over s squared minus k squared is cos kt. All right. So there's nothing really new in here. We just rewrite formulas backwards from last section. So any questions about this theorem? If not, let's just go to the next page. So let's just do some examples of finding inverse Laplace transforms of some functions. So the first example is to find the inverse Laplace transform of 1 over s cubed. Excuse me. So you just check the formulas on the previous page, and you found that t to the n is the inverse Laplace transform of n factorial over s to the n plus 1. So if you let n equal 2 in this formula, then you get t squared equals the inverse Laplace transform of 2 factorial squared s to the 2 plus 1 if you plug in 2 for n in this formula. So that gives us t squared equals inverse Laplace transform of 2 over s cubed, 2 factorial, which is 2 times 1, so that's 2. So if you divide by 2 on both sides, you can take out any constant from the inside and then divide by 2. So we got the inverse Laplace transform form of 1 over s cubed is just t squared over 2. So that's the answer. Any questions about this example? Okay, let's look at another example. Find the given inverse Laplace transform 2s minus 6 over s squared plus 9. Okay, so this time we're going to use the formula of sine kt equals inverse Laplace transform of k over s squared plus k squared. So anytime you see this kind of problems, to find the inverse Laplace transforms, you just check the function inside and see which one matches the formulas we have. Okay. And another formula we have is cosine kt is the inverse Laplace transform of s over s squared plus k squared. It turns out that we need to use both of them in this example. So in the first formula, let's just let k equal to 3. So plug in 3 for the formulas. We got sine 3t equals inverse Laplace transform of 3 over s squared plus 3 squared. So that's 3 over s squared plus 9 inside. And then again, you just divide by 3 on both sides, you get the inverse Laplace transform of 1 over s squared plus 9 equals sine 3t over 3. Okay, so you can see, you have matched the problem with the formulas. So the formula says s squared plus k squared in the denominator. So you have to rewrite 9 as 3 squared. And then you let k equal to 3. Similarly, if you plug in 3 for k in the second formula, we got cosine 3t equals inverse Laplace transform of 3 over s squared plus, s over s squared plus 3 squared, okay, at the formula. So again, it's 3 squared is 9, so that's just s over s squared plus 9, all right? So then the inverse Laplace transform of 2s minus 6 over s squared plus 9, we can break it up into 2. You break up the fraction inside into 2 fractions, and then that will give you Laplace transforms of 2 fractions, and then you can take out the constant 2 and 6 in each inverse Laplace transform. So we get 2 times inverse Laplace transform s over s squared plus 9 minus 6 times inverse Laplace transform of 1 over s squared plus 9. All right. So first you add 2s s squared plus 9 minus 6 over s squared plus 9, and then you just take out 2 and 6 from each inverse Laplace transform. And then we already got the inverse Laplace transform of s over s squared plus 9 is just a cosine 3t. So we got 2 cosine 3t in the first term, and the inverse Laplace transform of 1 over s squared plus 9 is just a sine 3t over 3, as we already got. So then when you multiply 6, 3 cancels here, so you're left with 2 in the second term also. So the final answer, so it's just 2 cosine 3t minus 2 sine 3t. All right. So you have to match the problem with the formulas, and sometimes you have to break it up into several terms and find the Laplace transform of each term. So that's example 2. Any questions about it? I don't see any questions, so let's just move forward. Okay, let's do another example. This time it's a little more steps, but essentially, we're doing the same kind of problem. So we need to find the given inverse Laplace transform of this function s squared plus 6 s plus 9 over s minus 1 times s minus 2 times s plus 4 in the denominator. So if you check the formulas on this, in this section, you don't find anything directly to apply to solve this problem. So, but we can always decompose a fraction into partial fractions, and by using the factorization of the denominator. And then we know there are 3 factors in the denominator: s minus 1, s minus 2, and s plus 4. If we can, decompose this fraction and rewrite the whole thing as a sum of 3 fractions using the factors in the denominator, then we get a over s minus 1 plus b over s minus 2 plus c over s plus 4. And we know we can always do that. Okay, that's a fact. So we got the equation of s squared plus 6x plus 9 over excuse me, s minus 1 times s minus 2 plus s plus 4 equal to a over s minus 1 plus b over s minus 2 plus c over s plus 4. So we want to solve for a, b, and c. We don't know what they are. Although we know there are constants, we still need to solve them. So the first step is just to multiply the least common denominator of all the denominators. So the least common denominator will be s minus 1 times s minus 2 times s plus 4. Okay, if you look at all the denominators in this equation, And that is all. Okay. You don't have to multiply another s minus 1 or s minus 2 or s plus 4 from the right side because it's already included in this common denominator. Okay. So just multiply this least common denominator on both sides on each term. Okay. So on the left hand side, the denominator just goes away. So we just got a squared plus 6, a plus 9. On the right side, we have 3 terms. And, when you multiply the least common denominator on each term, then you're going to cancel one of the factors individually. So for example, in the first term, s minus 1 will be canceled. So you're just left with the s minus 2 and s plus 4, and you still have a to multiply the whole thing. In the second term, the factor of s minus 2 is canceled. So you are left with s minus 1, s plus 4, and still have a b in the front. In the third term, s plus 4 is canceled. So we got c times s minus 1 times s minus 2. Now, then you can pick up different values of s and solve for a, b, and c. You can also, multiply out for you the right-hand side, for each term on the right side. You can FOIL it and combine like terms and then set up equations based on the coefficients of the polynomials on both sides. But the easy way to do it is just pick up some specific values of s. For example, if you pick s equal to 1, then you get 1 squared plus 6 times 1 plus 9 equals a times 1 minus 2 times 1 plus 4 plus b times 1 minus 1 times 1 plus 4 plus c times 1 minus 1 times 1 minus 2. All right. So you can see the second term and the third term on the right side just vanishes because 1 minus 1 is 0. So you just left with one term on the right. That's a times -1 times 5. Okay. If you do it, 1 minus 2 is -1, 1 plus 4 is 5. So then you get -5a on the right. And on the left, 1 squared is 1, 6 times 1 is 6. So you add 1 with 6 and 9, you get 16. So then divide by -5, you get a equals -16 over 5. Then you pick S2 from the original equation. So we get another equation. This time you can see the first term and the third term vanishes. Okay, they both have 2 minus 2. So at the end, you just got the term with b left on the right. So if you do it, you get the 2 minus 1, which is 1, and 2 plus 4 is 6. So b times 1 times 6 is just 6b. On the left side, you get the 2 squared plus 6 times 2 plus 9. So that's 4 plus 12 plus 9, which is what? 25. Okay, then you just divide by 6 on both sides. You get b equals 25 over 6. Then we pick -4 for s and plug into the original equation. We got both the first term and the second term vanish on the right side. They both have -4 plus 4 in the factor as a fact. So then you just left with the third term, which is c minus -4 minus 1 times -4 minus 2. -4 minus 1 is -5. -4 minus 2 is -6. So you multiply them, you get the positive 30. Okay, so the right hand side is just 30c. And the left hand side just the -4 squared plus 6 times -4 plus 9. When you plug in -4 for s, -4 squared is positive 16. And 6 times -4 is -24. Okay, so 16 minus 24 plus 9, you get a 1. Okay, so then you just divide by 30 to get C equal to 1 over 30. So we got all of those constants, A, B, and C solved, although they are fractions. So then we can go back to the original problem, and we take the inverse Laplace transform of the fraction. You can decompose those and the whole thing into 3 fractions as we already did. So that's A over S minus 1 plus B over S minus 2 plus C over S plus 4. And when you take an inverse Laplace transform, you can take the inverse Laplace transform of each fraction. Furthermore, you can factor out all the constants from the inside. So we get A times the inverse Laplace transform of 1 over S minus 1 plus B times the inverse Laplace transform of 1 over S minus 2 plus C times the inverse Laplace transform of 1 over S plus 4. And now you can put back A, B, and C into the expression. And we know the inverse Laplace transform of 1 over S minus 1 is just e to the 1t. If you still remember, the inverse Laplace transform of 1 over S minus A is e to the at. So if you let A equal to 1, you get the inverse Laplace transform of 1 over S minus 1 is e to the 1t, or just e to the t. Similarly, the inverse Laplace transform of 1 over S minus 2 is just e to 2t. And the inverse Laplace transform of S, 1 over S plus 4 is, you rewrite the fraction as 1 over S minus negative 4. So the Laplace inverse Laplace transform of 1 over S plus 4 is just e to the negative 4t. Okay, based on the formula. And then A, B, and C are just negative 16 over 5, 25 over 6, and 1 over 30. So then we got the final answer with those 3 terms. So this example takes a little more time because we need to decompose the fraction. But other than that, we just use the formulas for inverse Laplace transform. Any questions about this example? If no question, let's just go to the next page. So this time we want to do the derivatives, or the transform for derivatives. How do you find the Laplace transform of a derivative? So we're going to use a theorem here. It says if small f prime to small f to the m minus 1 derivative are continuous. So so this is strong condition. So we know how to find derivatives, but we also assume the function and its derivatives up to the minus 1 derivative are continuous on the interval from 0 to infinity. So because we are defining the function f of t with t greater than or equal to 0. Okay. So, and further, all of them are of exponential order. Okay. Remember what it means by exponential order? That means all of the functions can be or are dominated by some exponential function. Okay, that's what it means. And if n of t is piecewise continuous on 0 to infinity, so for the nth derivative of the f, we don't require continuous, but we do require the piecewise continuous. So that means this nth derivative of f may break up into pieces, but each piece is continuous. Okay. From piece to piece, there will be some jump or discontinuity. Then the Laplace transform of the nth derivative of f is equal to s to the n f of s minus s to the minus 1 times f of 0 minus f s to the minus 2 times f prime 0 minus da 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 minus f to the n minus 1 divided by 0. Okay, or capital Fs is just the Laplace transform of small f. So we know when we take the nth derivative of t, we get some function of t. Okay. So when you take the derivative of this nth derivative of t, you are taking the derivative of some function, and you should get some function of s. And it turns out the answer is just the polynomial of s, and we use the s to n times capital F of s, where f of s, capital F of s is just the Laplace transform of small f. And this can be easily proved by using the definition of Laplace transform and using the technique of integration by parts multiple times. Okay. And then you have to use the definition of improper integrals also. But we're not going to discuss that in detail in here. Just use this theorem or formula. So let's just do a couple examples. The first example says use the Laplace transform to solve the given initial value problem. So that's just to give us an example how to solve initial value problem by using Laplace transform. So let's just denote the Laplace transform of y, which we need to solve in this equation to be capital Y of s. Okay, so we know y is function of t, so we can take the Laplace transform of it, and we call this Laplace transform capital Y of s. We know it will be a function of s, right? So if you use the formula in this theorem with n equal to 1, then we get the Laplace transform of y prime. Okay, we are using y instead of f, but they're essentially the same kind of thing. So that will be equal to s to the 1 times capital ys instead of capital f s minus s to the 1 minus 1 times y of 0 instead of f of 0, and that's it. Okay. You don't have the other terms. So now then what happens is, the second term y of 0 is 0. So it vanishes. So what's left? It's just the s times y to the s. I mean, y of s, capital Y of s. So then, as we said before, we can take the Laplace transform of the equation on both sides, the differential equation on both sides. So if you do that, you take the Laplace transform of dy over dt, which is y prime. We got s times capital Y of s, as we already did, and minus the Laplace transform of y, which is just capital Y over s by definition, and equals the Laplace transform of 1, which is 1 over s, as we discussed in the first section. So we got an equation for capital Y over s, and you can factor out capital Y over s on the left-hand side, actually. So you get capital Y over s times s minus 1 equals 1 over s. So then you just divide it by s minus 1 on both sides, you get capital Y over s equals 1 over s times s minus 1. And again, you can use decomposition of this fraction into 2, which are 1 over s minus 1 minus 1 over s. And you can easily check this answer, but you can also do it by 1 over s times s minus 1 equal to a over s minus 1 plus b over s, and solve a and b from that by using the same techniques we did in the example on the previous page. But anyway, and that's what we get. So now we can take the inverse Laplace transform on both sides to get the solution y for the original problem. Okay, so what you do is just take the inverse Laplace transform of 1 over s minus 1 and 1 over s. And we know the Laplace transform of 1 over s minus 1 is e to the t, and Laplace transform of 1 over s is just 1. Okay, if you remember. So the final answer is just e to the t minus 1. You can also, plug in 0, using the formula of inverse Laplace transform of 1 over s minus a equal to e to the at. So you get the inverse Laplace transform of 1 over s equals e to the 0t, or just e to the 0, which is 1. Okay, if you let a equal to 0 in that formula. So you can see how we can use the Laplace transform to solve this initial value problem. Okay, so that's a brand new technique from the methods we discussed before. Any questions for this example or for this page? If not, let's go more forward to do another example to use Laplace transform to solve an initial value problem. This time we need to use the Laplace transform to solve the second order differential equation with some initial condition. Okay, so again, we do all the same steps. We let capital Y of S equal to the Laplace transform of Y, and we just use the formula on the previous page of the Laplace transforms of derivatives of function, for both y prime and the y double prime. So if you do that, you get the, Laplace transform of y prime just s times y of s minus s to the 1 minus 1 times y of 0. So plug in y of 0 equal to 1, s to the 1 minus 1, just s to 0, which is 1. Then we got s times y of s minus 1 for this. And if you use the formula with y double prime, we got the Laplace transform of y double prime equals a squared y of s minus s to 2 minus 1 y 0 minus s 2 minus 2 times y prime 0. Okay, so this time you do get another term. So just plug in those numbers. So we get a squared y of s minus s to the 2 minus 1, which is s to the 1 over s, times y0, which is 1. So we get s minus s to 2 minus 2, which is s to 0, which is 1, times y prime 0, which is 5. So you get a 5 or negative 5 in the last term. So now we can take the Laplace transform both sides of the differential equation and to convert the differential equation into algebraic equation. So just plug in the results we got for the Laplace transform of y double prime and y prime. So we got s squared y of s minus 1. No, I'm sorry. So you take the Laplace transform of each term on the left side. So then you plug in the results we already got. So we got the s squared y of s minus 5. That's the Laplace transform of y double prime minus 3 times the Laplace transform of y prime, which is sy times ys, y of s minus 1, plus 2 times the Laplace transform of y, which is y of s. And the right hand side is just the Laplace transform of e to the negative 4t. If we use the formula before in section 1, that's just 1 over s plus 4. So then you can, do a little simplification on the left hand side by multiplying 3 on the second part. You get negative 3s y of s plus 3, and then you just group all the terms y to the y of s, and the factor out y of s from those. You get s squared minus 3s plus 2, and then you just left with negative s minus 2 if you combine the constants also on the left side. So then now you can also move negative s minus 2 to the right, so it becomes plus s plus 2, and then you just add that with 1 over s plus 4. So I'm not going to show the details of that fraction. So you get a fraction, using the least common denominator s plus 4. And then you just divide by s squared minus 3s plus 2 on both sides. So at the end, what it becomes just, y to the s equals s squared plus 6s plus 9 over s squared minus 3s plus 2 times s plus 4. But again, you can factor out the denominator of s squared minus 3s plus 2 as s minus 1 and s minus 2. So the whole thing just becomes s squared plus 6s plus 9 over s plus 4 times s minus 1 times s minus 2. And then you take the inverse Laplace transform of the fraction. And this is exactly what we did previously, in this section. I think that's the problem, 2 slides before. Okay, so anyway, we already got the inverse Laplace transform of the fraction in here, and that's just negative 16 over 5 e to the t plus 25 over 6 e to 2t plus 1 over 30 e to the negative 40. So that just gives us the answer for the problem. So that's the solution for the initial value problem. Any questions? All right.